Okay, so today's video is on section 3.1. It's 3.1.2 again for the second day of covering 3.1. We're going to talk about one-sided derivatives. It's relatively minor, but a good thing to see. We're going to talk about deriving meaning from derivatives, which is a little bit more important, and identifying the graph of the derivative, which is probably one of the more important things that we are going to learn today. I'm going to start with one-sided derivatives, however, because they're a little bit more complicated. I want to hit that while it's fresh. So one-sided derivatives are exactly what they sound like. They're the derivative from just one side of the equation. You'll often see it like this. A function y equals f of x is differentiable on the closed interval if it has a different derivative at every interior point of the interval, and the limits below exist at the endpoints. Limit from the right side, limit from the left side. These can be considered right and left-hand derivatives. So where these come in useful are especially with piecewise functions, right? When we talk about limits only existing if the limit exists from the left and the right, sometimes those one-sided derivatives can be really useful. So here is a piecewise function. Now I could find the derivative from just the left side, and I could find the derivative from just the right side. But what I'm going to do here today is I'm going to try something instead. I'm going to just do a one-sided derivative. So the question is, The question is asking to show us that the function does not have a derivative at x equals 2. Just a graphical, like, yeah, that makes sense interpretation. Before we talk about one-sided derivatives, let's do that. I know this piecewise function is going to look like x squared before 2. It's going to look like that. And then it's going to look like 4x right after 2. So 2 times 4 is 8. It's going to start here and have a slope of 4, right? So if I look at that point, like pretty clearly it's not going to have a derivative there because derivative tells me slope of the function. Sorry about that. And like I'm not going to have a slope at that point because there's a discontinuity, right? I went from a value of 4, jumped all the way to value of 8 and just kept going. Right? Everywhere else I can find slope, like right at the bottom of that x squared, it's going to have a slope of 0. Here I'm going to have a negative slope because I'm going downward. There I'm going to have a slope of 4 because a linear equation of 4x, right? But right there at that discontinuity, it's not going to have a derivative because I can't say like, oh yeah, it's going up at this rate, or like, right, there's a problem there. To exemplify that problem with some algebra, we can use the idea of one-sided derivatives. In this particular case, I'm asking us to find the right-hand derivative for x equals 2. So the right-hand derivative would be this one, the derivative as h approaches 0 from the right-hand side. So we are going to find the limit as h approaches 0 from the right-hand side of f of a plus h, but in this case, my a is 2, 2 plus h, minus f of 2, all over h. And we're just going to do the math to kind of prove that, yeah, it's not going to have a derivative. It's not going to have a slope at that point. All right, so this would be the limit as h approaches 0 from the right-hand side, f of 2 plus h. Well, since I'm approaching h from the right-hand side, it's something bigger than 0. 2 plus h would be using this one when x is greater than 2. Right? Because it's 2 plus a little bit more. So plugging that 2 plus h into that function, I'm going to have, instead of 4x, 4 times 2 plus h, minus f of 2. That one, I'm actually going to be using this function right here. Because at 2, when the x is less than or equal to 2, I use that function. So I plug a 2 into there, 2 squared is 4, so 4, all over h. And then we're just going to try to find this limit. Now, I'm used to really nice things happening with this function, but I'm kind of anticipating, since I know the derivative isn't going to exist, right? I'm not going to have a slope at that point. I'm expecting a problem. So let's see if I've got that problem. This will be the limit as h approaches 0 from the right. Multiplying that 4 through, 4 times 2 is 8, plus 4h minus 4 all over h. I can combine like terms. 8 minus 4 is 4, so that'll be 4 plus 4h all over h. If I wanted to, I could factor a 4 out of there. I mean, I could try to see if it helps me. That'll be the limit as h approaches 0 from the right of 4 times 1 plus h all over h, but nothing's canceling out. Nothing nice is happening. If I tried plugging a 0 in, I'm going to get 4 times 1, I'm going to get 4 over 0, which is undefined. And nothing cancels out. So this limit actually does not exist. Since the limit doesn't exist, and the limit is the definition of the derivative does not exist at x equals 2. F prime of 2, remember that means derivative, does not exist. All right. At this point, I want to talk a little bit about why I care about the right-hand function. I could have tried the left-hand derivative, but the left-hand derivative actually would have worked. I'm going to show you why. All right. So to show you why, I'm going to go back to my sketch of the graph. All right. So when I talk about the limit as h approaches 0 from the left-hand side of f of 2 plus h minus f of 2 over h versus what we did, the limit as h approaches 0 from the right-hand side of f of 2 plus h minus f of 2 all over h. This is the one that eventually caused me a problem. Does not exist. And the reason it caused the problem is because remember how we've got this 2 plus h, where that's 2 plus a little something and minusing f of 2. And this comes from that slope problem where you're getting the 2 points closer and closer to being the same point. Well, when I did it with this one from the right-hand side, I was saying, all right, here's f of 2. Here's my f of 2 plus h, right? That's f of 2. That's f of 2 plus h. We're adding something to the right, 2 plus h. It's going to be over here. And that point, as it gets closer and closer to this value, it's not really getting closer and closer to the same point. It's just going closer and closer to that hole. So like this slope's going to be that, and then that, and then that, and the slope's going to get closer and closer to being undefined, closer and closer to a vertical slope, which is not really helpful here. So that's really that's not going to work. So that's why this one didn't work. If I had tried it from the left-hand side, and I can even leave it to you to try it on your own from the left-hand side, I would have actually gotten an answer from the left-hand side. Because from the left-hand side, see if I can get that. Let's do this in pink. Here's f of 2, right there. Pink's not showing up great. Let's pick a different color. Let's do this in orange. F of 2 is right there. If h was approaching 0 from the left-hand side, that means it's negative. And if I take 2 plus a negative number, right, 2 plus a negative number, that's actually going to land me over here somewhere on the left-hand side. And as this point gets closer and closer and closer to that point, the slopes are going to get closer and closer to a value. It's going to get closer and closer to whatever the slope is of just that left-hand side. So the reason I chose the right-hand derivative was because I knew that was going to cause me a problem. The left-hand derivative did not cause me a problem. If you had done it, I'll go ahead and leave you guys to try this one. It's a good practice. If you had done it, I would have found that this is equal to 4. But it doesn't matter if it's equal to 4, because remember we said the limit only exists if the limit from the left and the limit from the right agree. From the left, I've got a limit of 4. From the right, I've got a limit of does not exist. Those don't agree. Those aren't the same thing. So the limit as a whole does not exist. There is no derivative at x equals 2 because these do not agree. That one and that one. All right, not terribly important, but it can be useful. So you're going to have a couple of problems where you have piecewise functions. If you're not sure which derivative was going to cause a problem where it doesn't exist, I would just say do it both. Do it from the left-hand side, do it from the right-hand side. Worst case experience, you get extra practice. All right, now for the more important stuff, deriving meaning from derivatives. For that, I've got a graph here, f of x. that has an actual meaning associated to it. It says f of x shows the amount of money in Dave's bank account after x days. Right, so it says, hey, he's got some money. He started out with $200. He lost money or withdrew it until he ended up bottoming out right about here. What is that? Maybe 140-ish, 145. And then he gained some more money till he maxed out right about there, whatever that is. And then he lost some more or withdrew some, whatever it is. That's just a running account of the money he has in his bank account. All right. So to make sure we understand the meaning of a derivative, let's look at this. It says approximate the value of each expression below and provide a written description of the meaning of each answer. I don't know if you can see that in my videos covering it, but that's a word meaning, using correct units. So f of 40. F of 40 is just plugging a 40 in, right? So if I plug a 40 in, I land right there, which has a value of about, just over 150, it looks like, right? Let's change that from an equal sign to about equal sign. It's about equal to 150. Let's say 155. Now, this is asking for correct units. What is that a meaning of? Well, that when I plugged a 40 in, I got this value out, which is a measurement of dollars. That's the amount of money he has in the account at day 40. So my written description to be at day 40, Dave has about $155, right? But when I ask about f prime of 40, f prime of 40 is a derivative. And remember, derivative doesn't tell me a value, derivative tells me the slope. So at 40, I've got a slope that matches the same of the function, a slope roughly equal to that, right? So I need to approximate that slope. So I could say, all right, well, I'm going up and over. Let's see here. Let's use this one. So what is that? Oops. Up and over, right? Up and over, up and over. So I'm going a wide, let's see here, that went from 40 to 50. So that's a run value of 10. From here to here, that's roughly from there to roughly there. So not quite a whole step, not quite 50. So should we say, what do you want to say? 45, 40, let's say it's, you know what, let's go ahead and round it to 50. That's a pretty good approximation. We'll round it to about a change of 50. So that means it's going up 50 over 10, up 50 over 10, up 50 over 10. That has a slope of 50 over 10, which is a slope of 5. But just knowing that f prime of 40 is 5 isn't too terribly useful, because I want to know, like, well, what does that 5 mean? So let's think about that, those values as I was doing this up 50 and over. Oh, this one looks like I'm a little bit different. That's why it's an approximation. Let's actually change that. Let's say it's 20. I think that's a closer value of the actual one. So up 50 over 20. If I take 50 over 20, that'd be 2.5. It's an approximation. So either's fine. They're both roughly right. But either way, this 50 was a change in the y value. It was a measurement of dollars. So when I wrote that 50, it was really $50 over this 20. Well, that was a measure of the x value. That was a measure of the days. So it's $50 over 20 days. That 2.5 is $2.5 per day. So that's the amount of money, that's how quickly his money was increasing on that particular day. On that particular day, he was gaining money at about a rate of $2.5 per day. We can look on the graph and see he is gaining money, right? This was definitely, at this point, his bank account was definitely increasing. How quickly was it increasing? By about that amount of money, $2.5 per day. So meaning would be at day 40, Dave's account was increasing at about $2.5 per day. That 2.5 is a measurement of change, its slope. In this case, dollars per day. All right, I got a couple other examples like this. You might want to pause the video and walk through them on your own, because being able to understand them is going to be really important. And just me explaining it might not be super helpful. So if you want to do that, pause it, read it, give it a try. I'm going to actually just go over it to keep the video a little bit more concise, a little bit shorter. All right, same graph, this time new question. On about what day does Dave have the most money in his bank account? Well, here's his money, so the most happens right about there, which, I don't know, should we call that 65? At day 65. Find the value of f of x and f prime of x, use the correct units. All right, f of x would be when I plug that 65 in. When I plug a 65 in, I end up, oh, let's round that. That's not quite 300. Let's say 290. That's about $290. I was asked to use correct units, so correct units would be the dollars, $290. All right. F prime of x. In this case, I want to find f prime of that particular time, so I want f prime of 65. Same thing as before. But I got to remember what f prime stands for. That's a derivative. Derivative tells me slope. So at this particular point, when he reached the most amount of money, what was the slope of that function? Well, his money was increasing, then his money was decreasing. Right at that peak, you would have a slope that was exactly flat, right? Changed from an increasing to a decreasing. Right before you change from a positive to negative, you're going to equal 0. So that f prime would be 0. If I wanted units, again, it'd be $0 per day. When he reached that maximum, his bank account was changing at $0 per day. Before that, it was increasing. Then it started decreasing. That exact moment of time, he was not making or losing money till the next day. Then he started taking, then his bank account started going down. All right, last one, same thing. If you want to try it on your own, it'd be really useful. Maybe pause it, give it a try. I'm going to go ahead and go over it. On about what day is the amount of money in Dave's bank account increasing the fastest? So here he's losing money, not making much there, starting to increase. Oh, he makes a lot there, then peaks out, then loses money again. So it looks like he's increasing the fastest right about there, right? He's got a pretty steep slope there. So I'm going to say maybe right at that point. That's when it looks like it's increasing the fastest. Right? Seems to be shooting off in that direction. That's at about day 50. Day 50. So then I want to find f of 50 and f prime of 50. Again, f of 50 is just plug a 50 in, see what you get out. When I plug a 50 in, I land right here, which is like halfway-ish, say 225. $225. F prime of 50 would be the slope. So the slope would be how steep I'm going. I'm going about that rate. Let's see if I can count a rise over run, like up and over, up and over. I'm roughly going over 10, right? So that looks like 10. And up from here to here, that looks like from 225 to, oh, let's just say 325. That looks like up 100. So that's a slope of 100 over 10, roughly, which should be 10. And again, this is measured in dollars per day. At the most, his bank account was increasing at about $10 per day. All right. Last step with this video, identifying the graph of the derivative. This is a really useful thing so that you can identify what a derivative means. It's really helpful for understanding derivatives. So I've got a couple of graphs here. And the question is, which function, right here, which is f of x and which is f prime of x? So one of these is a measure of f of x, and one of these is the derivative function, f prime of x. We did a couple of these in the last video, but it's really good practice. We're going to do a couple more. There's a reminder, the values of the derivative tell you the slopes of the original. So maybe pause it, see if you can figure out which one's which. All right, in this case, that one's f of x, this one's f prime of x. I can tell because when I look at this, that whole area has a slope of 2, right? Up 2 over 1. This whole area, that's also linear, so it's got a constant slope. That's going up 1 over 3. So that's got a slope of 1/3. This area is flat. It's not changing at all. That's got a slope of 0. And this one's going down, so it's got a negative slope. Let's see here, down 3 over 3, that's the slope of -1. Down 3 over 3, right? Take a look at these values. That's a value of 2, just like that slope. That's a value of 1/3. There's a value of 0, just like that. And that's a value of -1, just like that. These values tell you the slopes of the original. Let's try a few more. Same question, which is f of x, which is f prime. Again, you might want to pause it, try it on your own. Again, remembering the values of the derivative tell you the slopes of the original. All right. In this case, the one on the left is f prime. The one on the right is f. The way I can tell, again, is by looking at the slopes of this one. Like if I looked at the slopes of this one, this is just a constant slope. This is going up, going up, going up, going up, going up. I should have seen a constant positive number if that was the original, but it's not. So that is definitely the derivative. I can confirm it by looking at the original, by looking at f of x. All right, just changing my color here a bit. All right, so f of x, if I look right here, I've definitely got a steep negative slope. Well, and that same value at -3, got a really negative value, right? If I keep going, keep going, keep going, the slopes are still negative here, but less and less and less negative, right? I'm still going down, but slower and slower and slower. Well, these values are still negative, but a less negative, less negative, less negative value up until right there, I've got a value of 0. And take a look at my original function. Right on that axis, I've got a slope that's 0. Right? If I look at these slopes, then it's going up, even steeper, well, positive value, even more positive, right? The values of this original tell me the slopes, the values of my derivative tell me the slopes of the original. All right, one more time. Let's skip this one just because we're running out of time. I don't want this video to be too long, but this might be one I'll try to do in the live class. Let's do this one and then we're done. Okay, that's another thing that this could be a really useful exercise, but this might be something I do in the live class. All right, use the graph of f of x to graph its derivative. Okay, so this is f of x. I want f prime. F prime tells me the slopes. So if I look here, that whole section has a constant slope, right? It's got a slope of up 2 over 1. So that entire time from 0 to 1, I'm going to have a slope equal to 2. So from 0 to 1, my derivative, f prime of x, is going to have a value of 2. Here's 2 right there, like that. Open circle, because again, right there, I'm changing from a positive slope to a negative slope, but I can't say exactly what the slope is at that exact point. So it's going to be an open circle there. We're going to talk more about that in next chapter. It's called a corner. We can't have derivatives at corners. We're going to learn that later. But an open circle there. And let's look at the next one. The next section, it's down 1 over 3. Down 1 over 3 is a slope of -1/3. Oops, sorry, not over 3. Over 1, 2. So that has a slope of -1/2. So during that entire section here, from 1 to 3, I'm on my f prime of x, on my derivative, I'm going to have a value of -1/2. Should be right about there. I'm going to just go like that. Again, using open circles. Last part, during this section here, that's completely flat. The slope of a flat line is 0. So during that section, right, from 3 to 4, from here to here, my derivative is going to have a value of 0. So that's what the derivative would look like. All right, now that I did that, I actually kind of want to go back to this one because it's probably a good one to do. Here's my f of x. I'm asking for the derivative. So the derivative tells me slopes. So I'm just going to pick some points. What's their slope right there? Well, that's flat, right? Slope of 0. So on f prime, I'm going to have a value of 0. What's my slope right there? Well, that's a negative slope. Looks like roughly maybe -1, -2, but it's definitely going down. So actually, let's Actually, you know what? Instead, let's pick them at points. Let's do it right at these tick marks. Evaluate the slope at each of those tick marks, or maybe the important parts. Without that tick mark, that's a negative slope, so a negative value. At this tick mark, that's going down even steeper, so a more negative value. At this tick mark, almost at a slope of 0. And I ran out there, so at this tick mark, oh, that's a really steep slope. That's going positive, right? It's a really positive value there. So positive value there. So it should look something like this. Really roughly, something like that. All right. That's a rough sketch. We're done. Again, that could be a really useful activity. Probably do it during our live session. Here is your homework. Good luck. As always, send me an email or visit my office session. I'd love to help you out. Bye-bye.